In keyframed animation, rarely are the joint angles or joint positions of a character edited directly. Instead, animators pose an animation rig, which is a system constructed in the 3D package that drives the underlying deformation and skeleton. Yet, animation research and technology almost always takes place in the space of the joint angles and joint positions. If animators wish to edit the results of these methods, they must first be mapped back into the space of the rig controls. Previously, this has been done with complex tools, or handcrafted scripts that take considerable time and difficulty to produce, and are specific to individual character or rig types. We propose a new approach for this mapping, which is generalizable and works in real time. We start by considering the rig function. This is the function in the 3D package that generates the joint positions given some rig attributes. We treat it as a black box and learn an approximation of the inverse using data supplied by the animators. Given a set of corresponding joint positions and rig attributes, we learn the mapping between them using a Gaussian process. But while this gives a good initial guess, there still exists some error in the positioning of the joints. We use Jacobian-based gradient descent to iterate closer towards an accurate solution. But the computation of the Jacobian in Maya is very slow, so we pre-compute the Jacobian for each pose in the animator data, and construct a Gaussian process that learns some Jacobian from some rig attributes. We will now show the results of our method. Here we generate new joint positions using a full-body IK system and map the results back to the rig controls interactively. We can also use joint positions generated from motion capture data. Here we show this applied to a humanoid character. The results can be edited interactively by animators. This squishy character has no skeleton, so instead we place virtual joints at each mesh vertex. We then perform soft body simulation on the character mesh to get new joint positions. These are mapped back to the rig for editing by the animators. Our approach generalizes effectively even for very limited input. Here we learn the relationship between rig controls and just 4 joints located at each of the character's feet. Our approach makes a sensible prediction of the character's whole pose. Finally, we show our approach applied to a facial rig. We place virtual joints at several vertex positions and learn the mapping. This allows us to move the virtual joints to pose the character interactively. In conclusion, our method provides a general and effective way to apply many techniques of animation research and technology in keyframed animation environments.